going over the perpendicular bisector, which creates circumcenter when they all intersect. And then we're going over the angle bisector, which when those three angle bisectors intersect, it creates the incenter. So we're going to start with the perpendicular bisectors. So perpendicular bisectors, what they do in general, it is a segment line, right? Any of those things, or point, and it is perpendicular to a segment, and wherever it intersects, that's the midpoint of that segment. So there's a theorem that is coming from our perpendicular bisector. It's kind of explained here, but any point on a perpendicular bisector is equidistant to its endpoints. So that's what we're about to go over here. So we have theorems with, okay, right, yes. Okay, on to the part that is now involving the triangle. So these perpendicular bisectors, when you have three of them, because you can have three perpendicular bisectors, one for each side of the triangle, when they come together, that creates the circumcenter. So a little bit of vocabulary. When we have three or more lines that are coming together, their point of intersection is called the point of concurrency. So yesterday you were looking at 4 different types of points of concurrency. Circumcenter, incenter, orthocenter, centroid. We're going to hit on circumcenter. Where it's going to get tricky is that each of those points of concurrency involve intersections of lines. So the picture of the triangle is going to look like just a bunch of lines. Depending on the different point of concurrency, we have all these different rules that are associated with it. So as we go through one, it might be like, okay, cool, I got it. We go through the other one today. Okay, cool, I got it. But once we go through all 4, and then I'm just giving you practice, and you have a picture of a triangle, and you're like, oh man, which one is it? I don't know. That's where visuals of having like pictures within our notes. So I'm going to go through, and I'm going to label like different things that we can do from circumcenters. So it's something just to keep in mind and like having your notes fresh. After we go through all of them, I'll give you like a page that just has all of it, so you can kind of reference it back and have one spot to look at it. But that's where it's going to get tricky, is that there's going to be a lot going on. So our circumcenter is create that theorem. It's created from perpendicular bisectors. So the markings of a perpendicular bisector. This is where we start. The blue is where we're starting. We have perpendicular bisectors, which means these are perpendicular. And we can say these are different congruencies. So that is our first marking. All of that is to generate P, because P is our circumcenter. It is created by perpendicular bisectors. Now the theorem that is associated with those circumcenters, it's using that theorem of the perpendicular bisector. When you have a perpendicular bisector, any point on it, so P is on the perpendicular bisector of FP, the distance from P to the endpoints of those segments are congruent. So, congruent like that. But that point of concurrency is a point that is on another perpendicular bisector. It's also on this perpendicular bisector of EP, which means P is also equidistant from C and B. So this one is also having that 4 tally marks. So what this is now showing, looking at this marking, what you can now conclude and kind of like memorize from it, if you have a circumcenter, so you know you have a circumcenter, perpendicular bisectors are proven, are shown. A circumcenter is always going to be equidistant from the vertices of the triangle. So the circumcenter to each vertice is going to be congruent.
The 2 on the bottom right, so those are like those are the same length as the one on the top.
Yep.
Then how is it that the point so far down? I mean, like,
because it's an intersection of a perpendicular bisector, and since we have Depending on the type of triangle, the circumcenter is going to be located in different parts. Because to create a perpendicular bisector, that was part of, yesterday you only had an acute triangle, but depending on the type of triangle you have, which is what we're about to look at it. But depending on the type of triangle you have, the location of this point of concurrency is going to change. Because when you draw, this is terribly drawn, okay. But if we have a perpendicular bisector, so let's say it's here, and then it has to be perpendicular to this one, so like here, and then perpendicular to this line, and here. So these lines are going to make it intersect outside of your triangle.
So when you draw the circle, is it supposed to be like?
So that's what we're at next. So I'm skipping one of. We'll go back to that other one. Depending on the type of triangle you have, so acute, right, obtuse, changes the location of your circumcenter. If you have an acute triangle, it's going to be inside. It's not directly in the middle of the triangle. It's wherever in that triangle, but it's going to be inside if it's acute. If you have a right triangle, it is going to be on the triangle. Specifically, it's going to be on your hypotenuse of the triangle. And then if you have an obtuse triangle, it's going to be outside of the triangle itself. And it's all based on those angle measures because the angle measures are changing where the midpoint of the line is of each segment is located, so you're having to extend that line out. This page right here, I would make a star with it. Like this is something that always, sometimes, never questions could come from. Like the circumcenter is blank in a circle, and you would put sometimes because the other options are on it or outside it.
You mean triangle?
Yes, sorry, triangle. Did I say, what did I say? Circle? Yeah, triangle. Okay, so that's something to keep in mind. So the thing that's always going to be true, though, what is always going to be true is when you have that circle triangle relationship, so you drew a circle with the triangles yesterday for two of them. For that, if you have a circumcenter, that relationship, so that circumcenter, when you have it as the center of a circle, the circle is always going to be circumscribed, which means the circle's on the outside, circles around it. So another added vocabulary word. Circumscribed means that circles are around it, and the vertices of the triangles are on the circle itself. But it's still having the circumcenter be the center of the circle. Okay. So now let's look at some pictures of the circumcenter within a triangle. So going to this next part. On this visual, how to know that this is a circumcenter. First thing, it says perpendicular bisector, which means we have the perpendicular bisectors that form the circumcenter. So going through and doing all possible labeling. We're going to do all of that before we try and answer any of these questions. So circumcenter, created by perpendicular bisectors. That means all of these things right here have a right angle associated with it. Just from knowing the word perpendicular bisector creating this, we can go through and do all of these labels. We also know that all of these are being bisected. So I'm going to go through and do those labels. So that means this is 26, that means this one's 22, and this one's 20. And then the last part, a circumcenter, is always, 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 it is equidistant to all of the vertices. So the last marking that we can make is that all of these are equal, congruent, which means all of those distances are 26.8. So the only thing we are unable to mark based off these congruency parts is the distance of the perpendicular bisector. But if we were asked, we've got a bunch of right triangles in there, so we could use Pythagorean theorem if needed. Okay, so now going through and actually answering all. MO, what's our distance for MO?
26.8.
Okay.
26.
And then PR, correct, is 26. And N,
40.
wonderful.
22.
SP is 22.
20.
QN is 20. And MP, 44. It's a lot of lines, I know, but like, it really is just practice of seeing them over and over again. And we're gonna have a practice day of just practicing all these once we see all the pictures and stuff, so we'll have some good stuff now. Okay, so I want y'all to do these two. Y'all do the next two. The ones that find in the distance of BG and GA.
How are you knowing where to cut the right angles?
How?
Mm-hmm.
Because perpendicular bisectors are always coming from the segments or the sides of the triangle. So if I know that it's a circumcenter, that means all of these lines that are in the middle of the sides of the triangles are forming right angles. So this is one, like this is stuff that you'll have to just kind of trust the labels, not necessarily the picture, because sometimes it might not look like a right angle. So this is definitely one of those situations of like not always drawn to scale. Trust whatever's given to you in the sentence beforehand, or like in directions or whatever is linked on there.
Oh, would G be a circumcenter in that thing?
Yes, G is the circumcenter here. It is inside the triangle because it is an acute triangle. So 9 for BG. G is also the circumcenter for this one. It is outside because it is an obtuse triangle, which B doesn't actually look that obtuse for me, but so I'm just gonna say it is. So 11. Okay. On to incenters. So incenters are made from angle bisectors. So now we're looking at things generated first from the angles. So starting with our angle bisectors, it splits your angle into two equal congruent parts, two congruent adjacent angles. What we're going to look at here is that if we have an angle bisector, we're going to be looking at the distance from the angle, a point on the angle bisector to the sides of the angle bisectors. Now thinking back to when we talked about distance between parallel lines, or like a point in a line, the part that was critical there is that when we get that distance, it has to be a right angle of the perpendicular distance. So as we're doing this in that theorem, what it's going to be saying is that this distance S, when you create a perpendicular line from S to the side of the angle, it's going to be equal on both sides, equidistant on both sides. So that's what the theorem is. The angle bisector theorem. We are given a point that is on the angle bisector, so we're given this point of D. When you create a perpendicular line from D to each side of the angle that it bisected, these are congruent.
Yeah.
You'll see.
Wait,
We'll get there.
why does it have two?
It could have one if one. It doesn't matter. I just wrote two on accident, so made it match. That's the theorem. The converse of it is going the other way, where if you see these markings on a picture, you can then conclude that this angle, or AD, the ray of AD is bisecting that whole angle of BAC. So converse is saying we have the angle bisector, and then the regular one is knowing we have an angle bisector, and then saying the same. So looking at next problem. So this is an example of what, not showing, there you go. This is an example of like what I would be wanting y'all to do with like, not doing a proof, but just validating of what theorem makes it true. So this one would be the angle bisector theorem. How you know that this one is good? Like how you know that this is showing an angle bisector because it's theorem. It shows congruency for your angle, and it is showing the perpendicular. That perpendicular marking has to be there. If it's not there, then it's just like, I don't know what's happening. So it's got to be there. So 5x equals 6x minus 5 is our angle bisector theorem. So x is 5. For the second one, it'll be the converse, correct, of your angle bisector theorem. Because you're given the markings that these are already congruent, those segments are congruent, which then means the angles are congruent. So 3x plus 5 equals 4x minus 6, so x equals 12. Y'all do the next one. So, knowing that x is 9, was that the theorem or the converse? Converse, right, because you already had the markings of the segments, not the equals. So, now for the in-center part. So, we looked at just the angle bisectors in general. Now to apply it with an in-center. So, when you have the three of them coming from the triangle, what we can mark. This is our picture. This is what our blank picture would look like. And we're told that we have okay, so this is what your marking would look like. So since it's an in-center, it's created from our angle bisectors, so those two angles would be congruent. These two angles would be congruent, and then these two would be congruent. From the angle bisector, the only segment that gets to be marked as congruent, the only segment word is the perpendicular line.
Did you unpause it?
Oh, yes. So that's the only segment markings that we get to mark as congruent. The angles get to be marked as congruent, which is different from our last one that we had, but as far as segments, that's the only segment. So this one's going to have a lot more of Pythagorean theorem have to be involved, because there's not things that are like all the same that are just connected the same. So the nice thing, or not, I don't know if it's nice, but the thing about a or an in-center, this in-center, when we make that circle on it, where it's that center of our circle, the circle is always going to be inside of the triangle. Always. This is not like a change depending on the triangle. When you create that circle, it is always going to be inside of the triangle. Specific for an in-center. And the vocabulary word for that is called inscribed. which is the one that reminds us of Harry Potter.
So there's inscribed and circumscribed.
Yes. It's kind of helpful to remember because, like, circumscribe, circumcenter,
Yeah.
inscribed, incenter. So the prefixes all go together. Okay, so on this next part, the markings on here. So again, going through the markings. How you know, because it doesn't say anywhere what kind of point of concurrency we have, but the markings on there is sufficient enough to tell you we do have a incenter. The reason, it's marking that these are congruent and it's marking a right angle, which therefore means those segments were created from our angle bisectors. So all of these angles would be congruent. And then solving for DG, that is this segment right here, but we know DG is congruent with FG. And then we have a triangle here where you have a hypotenuse and a leg, and you're missing that one leg, but you know it could be the same as DG, so Pythagorean theorem to solve that one. Do any of y'all remember some Pythagorean triples? Does that sound familiar?
Oh, wait, 116. Wait, so the hypotenuse is C?
Uh-huh.
Oh. It's just 5.
Since we were solving for a distance, we don't need to worry about the negative number.
So that's
Pythagorean triples, y'all never heard of those before?
no.
Okay, it's like a set of 3 numbers that are common for Pythagorean theorem. 5, 12, 13 is a common.
Why would it?
So if you see 12 and
So if you see 12 and 13, you know the third one is 5.
Or
Or if you see 5 and 12, you know the hypotenuse is 13.
it always is, or it's
Always, that is always. It's a Pythagorean triple. We'll go through later on in one of our other chapters, or there's a bunch of Pythagorean triples.
you don't even have to do the work.
3, 4, 5, Pythagorean triple. And so anything that's a multiple of 5, 12, 13. So if you had like 10, 24, and 26, that's 10, 12, 13, just all multiplied by 2. That would be a triple as well. So multiple of it. We'll have this day where we like look at, I'll give y'all a list of them. You can memorize them if you want to, or just solve it. I mean, it's not, y'all have calculators at this point, so. Okay, so I want y'all to try these 2. Yep. Go grab calculator if you want to, if you don't have one. Okay, y'all want to see a little shortcut? So, we know it's an angle bisector, it has markings, and it says find the value of x. So even if it doesn't have like every single marking needed, if it's saying to make n the incenter, then you can go through and make all the markings necessary. So these are all congruent, all those perpendicular lines. So your setup would be 4x and then 48 and then 52 for your C, right? Yes? Are we okay with that?
Oh, yeah.
Something to do with Pythagorean theorem. Before you solve this one, they're all divisible by 4. You see that? Pythagorean theorem does a little shortcut. If they're all divisible by 4, before you put them into Pythagorean theorem, divide them all by 4.
It's 200. Or, I mean 20. What?
Got it.
I got x equals.
Oh, because the 12 and 13 sides.
I got x equals 2.
So, if you didn't know that kind of shortcut, what you would have done is this squared plus this squared equals this squared. Where I see mistakes comes from this first one. 4x squared would be 16x squared.
Do square root.
Both parts of those terms have to get squared. So my guess, if you didn't get the answer at 5, that's where you need the mistake. You got to square x and the 4. Was that where you got messed up if you did? That's where I see the mistake that happens. So the same idea could happen on the next one. These are all congruent because we're supposed to be saying they're in centers. 51 is the NP, or yeah, NP. So 3x, 45, and 51. So that's your A, B, and C. So on that one, you could do the same trick that was before. Like you could divide all of these by 3. So then 15 and 17. And so that's what you can now do Pythagorean theorem with. And when you solve it, 8's your final answer.
Wait, what's 17 squared? 17 squared is, 256. No, that's,
No, 289?
289. I memorized.
I mean, if you remember that.
Yeah, it's 289.
Because my fastest sister could answer 17 from 17, which is in my second grade. She could get a dog, but she didn't know it. She missed it by like one number.
So close. 8, 15, 17 is another Pythagorean triple.
8, 15, 17.
Huh?
I'll give y'all a list at some point, but okay. The practice problems are not actually homework. They're just practice. If you want more, so like just something that if you want something to reference, like you want to study for the quiz, you just want to go over something, or you're bored over the break.